Well, hello everyone, and welcome to this outreach talk presented by Professor Stephan Roche. Before we get started, I would like to explain a little bit the context on this talk. As many of you probably know, this 2025 was declared the International Year of Quantum Science and Quantum Technologies. Stephan will later explain why this year is so important. ICN2 has been involved in several initiatives this year related to this special year and also related in general to quantum. One of the highlights was the Quantum Matter Conference held in France in June in Grenoble. It was organized by ICN2, Phantoms Foundation, and other institutions. And it brought together researchers and leaders working in quantum science. ICN2 was represented by several speakers, including some group leaders, and also the new spin-off, Apeiron Intelligence. We are also part of the master's degree in quantum science and technology here in Barcelona. Some of our researchers are teachers here. The students had also the opportunity to visit our labs and facilities a couple of months ago. We also took part during the year in other initiatives related to the International Year. Another example is the Quantum Days at the UAB campus. Here, the researchers and students had the opportunity to explore the most recent advances in quantum science. And also beyond academia, we have also been involved in several outreach initiatives for high school students and the general public. One example is this campaign. You have in this room these posters. This campaign is Quantum Science for Schools, together with other BEAST centers and the Perimeter Institute in Canada. We developed these posters and infographics trying to explain several quantum concepts and quantum phenomena, such as superposition, quantization, etc., but in a more easy and funny way, trying to, with this comic look. They were shared with several institutes here in Catalonia, also through the social media channels and website from the centers. And it was also it was presented at this exhibition here at the UAB campus related to the International Year of Quantum. And finally, we're really happy to conclude the year with this talk, where Professor Stephan Roche, leader of the Theoretical and Computational Nanoscience group here at ICN2, will guide us a little bit through this amazing world of quantum phenomena. So thanks, Stephan.
Okay, thank you. So thank you for being here. Before I start, I would like to make a disclaimer, because I don't know if it's Arlette or you, Chema, announcing this talk. You say outreach talk aimed at anyone interested in understanding the basics of quantum theory. So the problem, that's why we are here. Yeah. The problem is that this is a very famous word by Richard Feynman, is that nobody understands quantum mechanics. Nobody, even today. So that's very challenging to ask me to make you understand quantum mechanics. Okay.
I trust you.
Yeah. You challenge me. Okay. So yeah, quantum mechanics. It's a very strange word, in the sense that, surprisingly, our theoretical formalism can capture the deepest hidden law of the universe. That's kind of mind-blowing. And this actually enabled our civilization to make science fiction a reality. And progressively, you have seen that our society, the digitalization of a society based on information and communication, is becoming massive. So, fantastic. But at the same time, since the early days of quantum mechanics, we are still debating about the interpretation. we do not understand how to explain more intuitively this concept that out there you say you can explain in a funny way, right? The indeterminism of quantum mechanics, the duality between wave and particles, the superposition principle or the entanglement. All these concepts are really strange. And they are mathematical, they work very well, but we would like to have a deeper knowledge about that. And that has puzzled scientists since the very early days, and especially Albert Einstein. And this is the poetic way that Albert was trying to put this in perspective, his dissatisfaction about the way quantum mechanics was interpreted then and still today. So in the sense of the relay, I like to think that the moon exists, even if not looking at it. Okay. So think just a second. I will just go into a different way. In 1 billion years, it's likely that our species will have disappeared, or the sun will change and so on. So there will be nobody to observe this beautiful moon. The moon has no awareness of its existence. Well, then you can think about, so when there will be no human to observe the moon, is the moon existing really? Is reality of the moon makes any sense? But that's not actually why Einstein was having in mind with that. Really, the concept of reality is actually the key, the core of the problem, of the conundrum, of the interpretation of quantum mechanics. And I will come back to that, but one object that is so mysterious, which is the wave function or the quantum field, we'll see that later. There are two kind of opposite interpretation. One, which was the desire of Einstein, and the other one, which is more pragmatic approach, what's the Copenhagen interpretation by Niels Bohr, Werner Heisenberg, and so on. The realism is to say this object, which is a mathematical function, a quite complicated function, is actually describing a real physical reality, a physical reality. Okay? And beyond the fact that it's a mathematical object, it's not measurable, but the point is it can predict probabilities to observe things at perfection. So is it this wave function, these mathematical objects, telling you something which is real? Or, this is the other interpretation, it's not just a direct piece of reality, it's not just a very lucky mathematical tools which encode what we can access by our means, by our apparatus, about the reality. But there is something we will never be able to understand. So there is completely two different views of quantum mechanics. So now UNESCO has decided that we shall celebrate this year in 100 years of quantum mechanics. So what happened at the origin? We have to start with the Edison discovery of inventing this light bulb that have changed our way to illuminate the city and houses, right? Where he realized that by just driving a current in a very, very tiny filament of carbons, then at some point when temperature is very high, you emit light in all the spectrum. Okay, this is the black body radiation. So that was in 1879, and physicists have tried to understand this for a long time. And the early 20th centuries, the theory at place was unable to understand the experiment. Okay, the theory was actually predicting that if you go to very small wavelengths of your light, the energy density should go to infinity, which was absolutely not what was observed in the experiment. Actually, in the experiment, it goes even at zero value at some point in time when you go deep UV. So that was extremely puzzling for the physicists. Most of the physics thought that all the physics was understood at the time, but this was a puzzle. And to understand that, then comes Max Planck, first founding father of quantum mechanics. We realized that to give an explanation and to be able to reproduce this experimental curve, you have to make the assumption that light is actually composed by tiny objects, we will call them photons afterwards. So you have particles in light. Okay, and thanks to that, he can figure out this problem, this ultraviolet catastrophe. So that's the first man. The second man, which is very important, this guy who was working in the patent office, and in 1905, he published this this is like miraculous year, he published one of the papers that gave a Nobel Prize to him, which is a photoelectric effect. Photoelectric effect, when you shine light on the metals and you can detect a current. And actually people were puzzled because the intensity of the light was not changing the current, just the wavelength of the light. And Einstein used the concept of quantization of the energy, these photons, in order to give the full explanation of this phenomenon. That was depending on the frequency. Actually, very, very small frequency, wavelengths means very, very high energy. That's why at some point, the system cannot emit more light because there is no wave for him to emit this kind of photons. Okay, so we are still in 1905. We are not 25 years. Just before 25, just like unbelievable guy, in 10 years, special relativity and the general relativity. And I was discussing yesterday with Claudia and Jordi. I said, this is just mind-blowing, general relativity. The guy predicts that the matter deform space-time. This leads to the discovery of black holes, which is a gigantic singularity in the universe. But he has in his equation, and actually Einstein also mentioned that if you have space-time like a medium deformed by matter, you might have vibration of the space-time geometry. So you might have this kind of gravitational waves. But he made the math and he said, this is too tiny. Never we will be able to observe that. However, just a few years ago, thanks to incredible technology, we were able to detect this tiny motion of space-time due to the gigantic collision of two black holes billion years ago. Right? Just stop a moment. Can you imagine one guy make this prediction and then our technology was about to predict and to confirm this gigantic, event in the universe billions of years ago. So that's not quantum mechanics. Black holes, there is a big issue about quantum mechanics and gravity, but that's just like something I think is extraordinary. So we're still not in 25, we're the first Solvay conference, okay? Here you see plenty of men and there is one woman. And at that time, Marie Curie or Curie has already 2 Nobel laureates, one in physics for the discovery of radioactivity and one in chemistry for the discovery of 2 elements, polonium and radium. So she was a very strong woman, right? So at that time, we're still far from 25. We're discussing all the problems, the Max Planck and Einstein production and so on, and Marie Curie and radioactivity. I want to point out another woman who is also still before 25, which is Amy Noether. There was a woman who make a theorem that if you have a conservation symmetry, which is conserve a continuum symmetry, you have automatically a conserved quantity. And this theorem has an enormous impact in fundamental quantum mechanics, quantum field theory, and the standard model. And Einstein in an obituary was saying that was so far a genius since the education of women began. So I think this woman deserves to be mentioned. But then what's going on in 2025? These 2 guys in their early 20s, working completely alone, independently, and some kind of extremely high level of inspiration. One is Wolfgang Pauli, who explained that if you, there was an atomic model for the matter, which you have discretized energy level, but Pauli explained that there is a principle, which is called the exclusion principle, that you cannot put you cannot fill electrons in an arbitrary way, and they cannot occupy exactly the same energy level. So this principle is at the origin of the explanation of the periodic table, is at the origin of all the chemistry, right? So that's a massive impact into knowledge. The second smart guy is Werner Heisenberg, who decide to try to make some formalism to explain all these results. Okay, at the moment, it's just like observation, some kind of hypothesis, but it's not just like a basic formalism. And he was the first in this paper to bring a formalism, to bring matrix into the equation, and to be able to reproduce this atomic spectra and so on and so forth. And then he started to point out on something which is very weird from a classical point of view. That, for instance, there is non-commutativity between position operator and momentum operator, which means that if you measure the velocity, the position and the velocity of a quantum system, it's not the same that if you measure first the velocity and then the position, or vice versa. There is something which is very strange. non-commutativity. In addition, it comes with a law, which is you cannot have an infinite precision accuracy on the position and the velocity of a quantum object. This is a certainty principle. So these are really like major events in 2025, where people think that really the foundation of quantum mechanics is already there, and then things will move forward fast. 2027, this is the most famous Solvay conference, where you have two-thirds of these people who get the Nobel laureate. So you have these two gentlemen, Pauli and Heisenberg. And actually what happened is that during this conference, one of the key results is a big debate between Albert Einstein and Niels Bohr about the interpretation. And Einstein making a lot of Gedanken experiments, thought experiments, in trying to disprove what people are starting to predict to this new world. But there is another guy who is worth pointing out, Erwin Schrödinger, that you have heard about, because he's the first one to give an equation that is a kind of very aesthetic equation in order to explain how these quantum particles propagate in time and space. And this point out really one of the main concepts, which is this duality between wave particles. Also, it's well known to try to make an image to see how complicated or counterintuitive is the superposition principle. Because superposition principle means that you have a quantum state that actually exists in two contradictory possibilities. Okay, it cannot be dead or alive at the same time. Okay, so in classical physics, if you are in this example of the cat, you open the box, it's dead or alive. But in quantum mechanics, and if you don't open the box, the cat is still dead or alive. But in quantum mechanics, the state will be dead and alive at the same time. And they are manifestations, they are observable due to this superposition principle. So that's kind of also already mind-blowing. And one of the experiments that really unveiled this superposition principle or this wave particle duality is this experiment where you have a double slit, you send a single electron, and they have two possibilities to go through, and then you expect, because they are particles, that you will have two different impact zones. But the experiment shows something very different, actually. The experiment shows that when you send one particle, indeed, it seems to hit somewhere. But then if you send enough, you make a statistics, you will see some interference fringes that actually tells you that a single particle is going at two different locations at the same time. You cannot explain otherwise. And that doesn't make sense. For a single particle electron, you would say, okay, that's a wave particle, something like that. But what becomes more surprising is if you send fullerene with this double slit, or molecules, big molecules that even vibrate. That's something that has been shown also recently, is oligoporphyrates. So you have something and it interferes with itself. So you still have this kind of interference pattern of gigantic object. And then people try to go bigger and bigger and bigger. At which time do you lose this quantum mechanic awareness? That's something that has been published just a week ago or 2 weeks ago by a very famous Chinese experimentalist. He made an experiment in order to disprove one of the Einstein thought experiments, which is a double slit, but with another slit that is movable. And so Einstein say, I can have a thought experiment to show you that you can measure at the same time the position and the velocity. And just this year, 100 years after, this is a definite proof that Einstein was wrong. This indeterminism, this duality is really there, and you cannot measure simultaneously the velocity of the object and its position. But it had taken 100 years. So that's to show you that really, wow, that's really a complicated concept, and it takes time to figure out what's going on. More with this, and then we go to spin. This is something we love with Sergio. So this is all a picture of the atoms where the electrons move around the nucleus. And there were some, measurements of the mass or the charge of this tiny electron, which is considered as a kind of point. Of course, quantum mechanics showed that the spectrum of the system is discrete, it's complicated. But then, if you put a magnetic field, you split the levels, and that was a very surprising thing. So, actually, the prediction first there was some kind of heuristic interpretation of the splitting. But one guy was a student of Einstein, Otto Stern, a chemist, student of Einstein. So student of Einstein, he didn't believe into the interpretation of quantum mechanics as the standard interpretation. So he tried to make an experiment to disprove quantum mechanics. And he made the Stern-Gerlach experiment, where with a beam of silver atom going through an homogeneous magnet, and you expect, if quantum mechanics is disproved, that you will have this kind of mark on the screen. But what he observed, unfortunately for him, is not that. It's a surprise, and actually what he observed can only be interpreted by bringing a new degree of freedom into this single particle, the spin degree of freedom, which can be in a up or the down situation. And what is also very weird is that this tiny, let's say, intrinsic magnetic moment looks like if the electrons were spinning around itself. Okay, but it's not a good image. It doesn't make sense, even if it looks like that. So you have to wait for a deeper level of quantum mechanics, this is quantum field theory, in order to fully understand what is exactly the spin, or it behaves. And also, major achievement of Paul Dirac is in one equation, which is kind of generalization of the Schrödinger equation, he can also come up with a prediction of the antimatter, which then has been confirmed experimentally. So this is a simulation we have made, and I say this like quantum mechanic weirdness up close, because the spin, initially people say, oh, it is with the electrons, okay? So it's like there is something weird, and the electron is moving and the spin is moving around that. But what we see here is a kind of electron which is, let me see if I can do it again, that you have initially an electron that injects in the polycrystalline graphene, and then you look at what the electron is doing. So the electron extends in all space, or where is the electron? And then the spin kind of also distributes in space and then oscillate. And if you want to measure it, you have to make some measurement, and then you will see, for instance, that if you have initially in one direction, it will be damped to some relaxation phenomena. So where is the spin in real life, in real time and in real space? It's purely, you can project it with your mathematical object, but you cannot make sense of it in terms of a classical, of a motion, of anything. So spin is very important. This is the last big computer at IBM not using semiconductors, using vacuum tubes. And what the guy is showing here is where the data were stored. Okay, it was like magnetic disk. And at the time, it was like $10,000 for 1 megabyte. So you have 5 megabytes, this big stuff. So then, many years after, thanks to the miniaturization, let's say, of the magnetism, making things very tiny, Albert Fert and Peter Grunberg could predict a phenomena where this is really these individual spins that are crossing a very tiny interface. And depending on their polarization, you will have a change of the resistance. And so kind of going to nanotechnology, and their prediction then has been confirmed. And this has given rise to a lot of application. So by the way, Albert Fert is still in our advisory board of ICN2. So there is spintronic everywhere. Everywhere. There are spintronic elements like compass, like memories, in a lot of application. I think this is a slide I borrowed from Sergio. Sergio, you recognize maybe all the things you do. And I realized just a month ago that the slide of Sergio actually was very interesting for me because of this. And this needs magnetic sensor in order to make very, very precise surgery. And it turns out that 1 month ago, I have the chance to be here and to be in person in contact with this robot coming. I didn't see him coming to me, unfortunately, but I had the chance to get a special interaction with the robot. And after the operation, I was in the room and I was reading books of quantum mechanics, of course, in order to think about the presentation. So yeah, thanks to Spintronic, I was safe. So this ends the first quantum revolution. Okay. First quantum revolution, because all I said actually has spread into computers, into laser photodetectors, and so on and so forth. So this concept of quantum mechanics I have explained so far are massive into our digital technology. Now, again, the question of reality comes back. And again, this discussion about there is an independent reality, independent of the observation or not, is coming back again. And I just one slide to explain what's the puzzle here. The Schrödinger equation is something that actually is called deterministic. If you know the quantum state at some point in time, by using this equation, unitary equation, you evolve your quantum state, and then you can predict at some point before making a prediction, measurements, you can predict what kind of result you expect. But the problem is when you make the measurements and you get an outcome, there is no way to understand this transition. It is just a postulate. You will measure one of the possible expectation, but you have no way to understand why. You assume that it's completely indeterministic. There's no reason why. So it's like God played dice. It's like pretty much Einstein. Okay. So Einstein didn't like that. And in 35, so 10 years after the 25, he counterattacked, okay, or strike back like Star Wars. Okay. And now it comes with something which is a new idea, a new thought experiment. This paper is very easy to read, actually, where it takes two particles. And then, thanks to a kind of thought experiment, he said, your description of quantum mechanics is not complete. Why? Because I can find a situation where I can predict with certainty a result of an experiment. And if I can predict with certainty, it means that there is an element of reality that is hidden. So you are missing hidden variable in your formalism that if you add them, you will understand everything and you will lose this randomness, which is very weird. And Schrödinger came with the word entanglement to explain this kind of very fuzzy concept. Actually, Einstein was really, pushy about that. And he used the word spooky electron distance. He cannot understand how something, light years away from another, if measured, can influence automatically, simultaneously, what would be measured extremely far away, because it violates locality, special relativity, and so on and so forth. So he has been all his life trying to find arguments and to try to explain things deeper. So let's also just visualize this a bit. Once in the vision of this Einstein, you take two particles, they are together, entangled, we'll see what it means entangled, then you separate them apart, and then you will measure, for example, the spin. When you make the measurements of the spin, you have no way to know if you will measure the spin up or down. It's a two-valuedness quantity. No way, it's probabilistic. So no way to predict. So that's indeterminism. But then when the system is really entangled, when you measure once, the other is automatically defined. Although it will be measured, the person that will measure it will see it's random. Plenty of entangled particles are split apart. And every time I measure on my side, I see it up, down with some probability rule, like 50%, let's say. But if I measure up, I know the other guys in the other part of the galaxy will measure exactly up or will measure down with certainty 1. Although he has no clue about that. But he can do the same. Once he's measured, he knows that me at light years away from the galaxy, I measure the same or the opposite. So this is non-locality. There is an information inside this quantum state that is spread everywhere. And when you read it everywhere the same. So that's kind of a collapse of this object, which is taking place. And that's the fact that information is distributed in space and time. So, okay, you need a guy to push this further. And this is Bell, is another theoretician. 35 years later, after the paper of Einstein, proposed an inequality and an experiment in order to discriminate between the theory of Einstein, which is it's incomplete because you have some missing variable, and the traditional explanation of quantum mechanics, which is no, it's more complicated. 15 years later, this French guy who is doing his PhD and is completely stubborn about trying to make these measurements of in order to test this inequality, finally succeed. It's not the only one, but he's one of the most famous one. And finally found that indeed the result of this experiment demonstrate that the idea of Einstein that is something incomplete is wrong. It's complete. It's just like the problem is that you have to accept this non-locality, which is extremely a weird concept. Something. So this is like the book I was reading in the Val d'Eblon, and it's a very nice book. It's written in French, but he explains all the story, all the fight he has to do in order to make this experiment working. It's just a fabulous book. Okay. So let me continue. This guy and others, they got the Nobel laureate for this, okay, for making these experiments. And this is this year, right? We have other Nobel laureates. That's another French guy. And these Nobel laureates, actually, for some work they did on superconducting circuits that make like artificial atoms, and they are such foundational for what we call the quantum bit, the qubit. Okay. And one of them is actually CTO of a company that is creating quantum computers that you may have heard. So quantum bit and bit of information, I'm trying to go quite fast. You know, all our digitalization of technology is based on the classical bit of information. So you have 1 and 0, right? So you just have two possibilities. When you go into the quantum world, the qubit is not just 2, it's kind of infinite possibilities because your arrow is actually moving along a sphere. Okay, so you can have north poles, south poles, but everything in between. So I have plenty of possible position. So you have possibility. This superposition is really intrinsic to this qubit, so you can superpose them. So it can be up and down, for instance, in some percentage. You can prepare that, and then they can be entangled. It means that they can have correlation between themselves at long distance, and when one is doing something, everybody is doing something correlated. So that's the idea of the non-locality. So now today you have companies that are building this quantum computer, and this is an example of IBM, which is has this big equipment, and then at the end it's very tiny, but you need to cool this down because it's superconductors and so on, and you make these things that are real. And with that, what do you do? With that, you want to do something that is really disruptive. You want to overcome the limitation, for example, classical computing. So just what is the point? So in classical qubit, okay, if you have, for instance, 3 bits, you have 8 possibilities, just 2 to the n. Okay. So in qubit, you have the same. If you have, let's say, 300 bit or qubit, you have 10 to 300, so it's more than the atom in the universe. The difference between classical and quantum is that in classical, you have just 1 out of these infinite numbers of possibility. But in quantum, you have all of them together into the wave function. They are all there, all the possibilities, and they evolve in time, and they can interfere, and they can destructively, constructively. So it's gigantic parameter space where you can play and design some quantum algorithm in order to solve some very complicated, problems. Like, for instance, you want to factorize the prime numbers. So that will show, and so on and so forth. So that's the difference. In one case, 300 bits, okay. You have plenty of possibility where you would just have 1. With a qubit, you have all of them together, and you can play with them. Now, thanks to this rising of entanglement of qubit and quantum computer, there is a lot of expectation, a lot of company, and a lot of investments, and a lot of prediction that with a big enough quantum computer, you will solve almost any problem, like the climate change, like, you will find new pharmaceutical products and so on and so forth. So of course, for this company, they play with the hype in order to get public funding and so on and so forth. But some people are more reasonable, and for instance, this is a Feynman chair at Caltech. He say, hey guys, be careful because we are not yet there. Okay, and at the moment, this big computer, what they can do more or less is to factorize a prime number of 2 digits, right? You can do it, and 5 years old maybe can do it. So it's not that fascinating at the moment, but it's kind of unstoppable. And what we can do things now with this computer. We can make some kind of academic model and see some phase, topological phase that were predicted, but with this kind of instruments, you can kind of materialize them. This is something also, we're still an archive, which is also very funny because with this computer with 156 qubits, but actually it's just using 5 logical qubits to make this working. According to the paper, they have made kind of tests, we go fast, and they demonstrate that the wave function is a real physical thing. Okay, so it's still there. I mean, the debate about ontology or epistemic interpretation of wave function is still subject to experiment and to debate. So that's just in passage. So a lot of investment, a lot of interest in quantum, especially in Europe. I will go fast on that because I want to come back and then I want to go to ICN2. Where are we? What are we doing in this big picture? But I want to come back to this ultimate reality, and it's almost philosophical. And this is an interview just like a few weeks ago about Alain Aspect with Brian Grimm, an expert of string theory. And actually he say, okay, you sit on the ball on the Einstein side, okay? And he's sitting on the Einstein side, actually, okay? That objects have a physical reality independent of the observation of the apparatus. This is what he said. What kind of measuring apparatus you use, but then you have to accept the quantum non-locality. Okay. You keep the realism of the concept, but then you accept that non-locality, which looks very weird when you speak about these two split apart particles, is real, is existing. Okay. So personally, I sit on the second side, that is, I still think object with a physical reality can be influenced at distance instantaneously. So, but then I have to accept the idea of non-locality. Okay. Now, this is like the craziest slide of my talk. Hey guys, you're speaking about split particle apart, but particle, then there is an additional layer of quantum theory, which is quantum field theory. And in quantum field theory, particles are excitation of the Dirac field. Okay? So they are field. And fields are omnipresent. They are everywhere. Okay? So particles are not just like tiny stuff that you can separate. They are excitation of the field. And in vacuum, there's nothing. It's empty. No, it's not empty. There are fields everywhere. And so you can, and energy, but you can take part of the energy and create matter, like matter and antimatter for a very short time. And what is fascinating, I've always been fascinated by Casimir effect, that thanks to this, that the quantum fluctuation of the vacuum can be detected. Okay, you have two plates, the conductors, and because the strength of this fluctuation are different inside the cavity and outside, there is a pressure that pushes the two plates together. And this has been predicted and measured in emptiness of matter. So that's the crazy slide I said. Are you surprised about non-locality if you forget to think about split apart particles, but you just think about fields? So if there are fields omnipresent everywhere, they can communicate. I mean, they are everywhere. So it's kind of you have automatically break the notion of locality. So I don't know, and we have plenty of equations in the universe. Also, I wanted to show something about entanglement and locality. Sorry, this is like the slide maybe going a bit more crazy. There is a very nice superconductivity. It's a beautiful phenomenon because then you have no dissipation in the system and you do not waste energy by isolating, right? And what happened in this superconductivity in the BCS theory is that you have two electrons which are entangled because they are like this, they're like this, and they can be far apart, actually, 100 nanometers apart, but they are still, creating a kind of a particle, a boson. And what is interesting is that this entanglement is actually driven by a source, by the vibration of the system. So you will say entanglement is related to something that vibrates and that should be there. Not really. You can split this particle apart. They are not in the same medium. There is no modulus vibration that here to sustain entanglement or non-locality, but still non-locality exists, and this has been measured. And more things. And there are more exotic particles that have been predicted that eventually could help to do some kind of new paradigm for topological quantum computing when you have a kind of error without error computation. Okay, now I want to come to ICN2. So we're doing what we're doing at ICN2 in quantum. So it was a trending topic. We are doing materials. We are creating materials, growing materials, okay, or fabricating some materials. And then we are using those huge equipment, like in all these labs, to measure them. This apparatus that will look at the property of those materials. So that's just and we have a quantum synergy lab. So quantum is present into the ICN2. And in addition, I think one thing that characterizes it is that we use quantum technology. I mean, we want to explore new quantum technology based on this understanding of new quantum materials, especially topological quantum materials. So in particular, in quantum topological quantum materials, we have graphene, topological insulator, and other things. Okay. And these are Nobel laureates that got that made some advance into the topological quantum materials, topological quantum fields. And this guy is in the advisory board of ICN2, by the way. So graphene, everybody has heard about graphene. So in the tip of a pencil, you get this wonder material, which is just a layer of carbon atoms. Those guys got the Nobel Prize because it has fantastic properties. And yeah, it has fantastic property in the sense that this one is the most mind-blowing, is that this Nobel Prize said this is the only materials that you can go from a quantum field theory to patentable application. What does that mean? Quantum field theory, again, it's a very complicated description of matter-light interaction, again, Feynman, and one major quantity, was you have speed, velocity of light, h bar, and this is a fine constant, structure constant. And this is very complicated to compute. But with graphene, you just look at an optical contrast and you can deduce its value. And it's just, what? So there's an analogy between high energy physics and the physics, low energy physics of graphene and high energy physics of particles, which makes you to be able to measure the fine structure constant just by looking at the opacity of a graphene. So that really, for me, it's really crazy. This picture was taken at ICN2 before Adrian left to ICREA. And that's also was fascinating feature, where it is suspended just a monolayer of carbon atoms. This material has very specific property, okay? Like he has plenty of degree of freedom inside. It's like the particle, when the electron is on graphene, is different, His mass is 0, effectively, so there's no mass, and he has more degrees of freedom. And actually, these more degrees of freedoms, they have an impact on the observable. And this is something we found with a collaborator with Sergio and things like that in the past. We found that the relaxation of the spin is actually driven also by the entanglement with intraparticular degrees of freedom. But graphene is also very fascinating because of the application. You can make a plastic conductor by just one layer of graphene, okay? Or you can make people happy, like Costas and Jose Garrido, and they get prizes and make spin-off, and thanks to graphene. So they have to be knowledgeable to the magic of these materials, and also to quantum field theory, because it's certainly useful for the Rayleigh plan. Okay, this guy is maybe a possible Spanish physics laureate in the future. Why? The guy just put 2 layers of graphene, and then he rotate a bit, one on top of the others, start to make some kind of twist tonic, and then thanks to that, he discovered a completely unexpected superconductivity in the system. Completely mind-blowing. So, great. So that's a paper we published with Pedro recently, where we're the first to look at what's going on. If you take into account some disorder and you do not break the flat bounds of the magic and things like that, we can do some theoretical stuff. Now I put Sergio because Sergio has a big challenge, because there are thousands of different 2D materials that you can assemble and you can rotate. And so you have an infinite possibility. And Sergio is an expert of manipulating spin. So Sergio is fighting in order to find the best combination and so on. But after 10 years of work with Sergio, we could explain to the industry and the company, what can you do with 2D material in order to advance non-volatile memory technology, the things that Albert Fert has pioneered. So you can really do something great, potentially, with these materials. It's big. So we also Jordi, where I was speaking about topological quantum computing, and Jordi, together with Microsoft and other people for years, they are trying to implement these very weird exotic particles that you can, manipulate, they are entangled and so on and so forth, to design new kind of computer. It's very, very complicated, but anyway, why not? With Jordi, he's also working and collaborating with all the groups creating qubits based on silicon or germanium materials. Okay, so these are silicon germanium qubits which are fabricated in a foundry in Copenhagen, and these are TM pictures taken by Jordi Arbiol. And what we have recently done with Pablo, Jordi, all the group, Mark Potifol, Thomas Galvani, and so on, we have tried to create digital twin of these qubits using artificial intelligence, and then we are trying to simulate the property of this digital twin in order to help the optimization of the technology, right? So that's something I'm going to do a bit fast. That's a very new area that could be very important and have a lot of impact. So I'm taking ITER, and because it's also extremely interesting to go and to probe quantum phenomena at the atomic scale, right? Or to create new materials like this kind of ribbons or the porous nanographene in order to control all their properties, like transport, spin, or optical property. So that's what they are doing in the lab. The lab is Klaas and Roshan. They are using, they're trying to shine light in materials and see and track the ultrafast dynamics in these materials, which is also revealing something, a new world of possibilities for optics detection and photodetectors. Taking the group of Javier with Mariana, where they are trying to understand the thermal property of this material, especially when you start to assemble them and to rotate one on top of another and so on and so forth. So, actually the possibilities are infinite in terms of fundamental studies. Pablo is an expert of this field, and you need simulation in order to go deeper into the understanding of quantum. Pablo is really very well known and very active into bringing computation at a level of realism that is the most perfect possible. Okay, we're also working on this. We're doing a different track from Pablo, but we are simulating device and looking at materials and so on. And recently we have been using artificial intelligence in order to accelerate the design of new materials, also simulation with Jose Hugo. Okay, there are plenty of questions. Actually, all these materials that we are studying at ICN2, they might be able to provide new paradigm for quantum technology. And there are plenty of questions that are, still to be answered, where maybe one day some group at ICN2 could bring a solution. Now, again, I'm coming back to that. And one of the questions, a kind of priority question is there a hidden physical mechanism that could explain the wave function collapse? Because as I said to you, the moment of the measurements, we have to forget about all the very deterministic evolution of the quantum state, and we have to make a postulate, and that's really a problem for the interpretation. Okay, what actually happening? And for 100 years, almost 100 years, people have said, no, shut up and calculate and forget about this projection of the quantum state. So this is an interesting case. Roger Penrose, he got the Nobel in 2020 for his work on black hole. But he said that if the state is superposed, it means that you might have kind of mass delocalized in two different spaces. And that's very weird. And that should provoke the collapse immediately. So he tried to put a physical mechanism that will explain the collapse. He even evaluate the gravitational self-energy and a kind of time to collapse and so on. And some people are doing experiments in order to test this. It's extremely weird to think about the superposition like associated with some local mass, which is distributed, because the mass of the electron is one, right? As I say, the spin is one, and it can be distributed in a mathematical sense, but trying to make a reality of the distribution of mass is extremely weird. So it's super controversial. Or 2 cents of what we did with Jorge and others. We come back to the Sterner-Gerlach. In the Sterner-Gerlach, you have your incident wave function, and you split it with a magnetic field, an homogeneous magnetic field. And so your wave function can be here, your electrons can be here or there. You don't know. And then you hit the screen and you have a certain probability to detect it here or to detect it there. This is a Stern-Galac. It can be up or it can be down. But the quantum mechanics say, hey, you don't know what happened, you detect it up. Yeah, but you detected something happened. There is something. The screen interacts with something coming, right? And this you take out of the equation completely. That's real. Why don't you try to bring into the equation? Because this is really play with God. You just have the probability, it's random, total random, and there's no absolutely microscopic mechanism at play, which is not the reality of the stuff. And this is where put our 2 cents. We say, no, there is something. There is an interaction between these incoming strange things that can be real, with some fluctuation maybe of the screen that are inhomogeneous, and maybe this very small difference in energy might materialize the quantum state in a place or another. So we published 2 papers with Jorge and then with Luis. So it's kind of, you publish this and you wait for 30 years or 40 years, and maybe someone will say, wait, let's use this to go a little bit further. But that's kind of obsession to say that's weird to stop at a postulate when this is kind of, at the core of what is reality. And if you make a measurement, you make something real. And something happened before and something happened during and after. So it should be something to describe, an interaction to describe this. Okay. Another thing is we also play with entanglement. We, as I say, there are many degrees of freedom into graphene. So we actually did some work and find some kind of strange time-dependent bed inequality. We submit to PRL, and it was interesting because the guy said, "Oh, it could be very, very important if you demonstrate that it can be implementable and have some technological relevance. But for the time being, we don't know. So go to PRV, rapid communication." Yeah. And we make it a bit better with Jorge because here we really make a connection between the spin relaxation and the entanglement. And we found a deep relation between both things. Anyway. So the dream of David Bohm and John Bell, because they developed all the theory, was based on measuring spin-spin correlation. So far, ASPE measurement is only on measuring correlation between polarization of photons. But to date, there have been no ever Bell's inequality violation experiment using fermions. Okay, nobody has never succeeded to do that. So that's the dream of Bohm, of John Bell. I mean, they passed away, unfortunately. That's also my dream, and I would like and maybe this guy could do it, but Sergio could explain. It's too complicated. It will take years, a lot of money. I don't know. But Sergio say no, forget about me. I'm going to different ground. But these 2 guys, they could do it. And I think, frankly, imagine you could do with all that I say before. I mean, all the talk is to motivate you to do the experiment. Actually, all the rest is pure, just like theater. Yeah, when I become rich with a payment, I will find it. That's the idea, because I submitted in IRC. I failed a couple of times. But fortunately, thanks to this failure, when we are asked to in one day to produce 1 page for the quantum communication program, we put part of this stuff, and we got almost €1 million to get our quantum synergy lab. So at the end of the day, your failure can be converted to success to some degree. Okay, that's the last slide. It's Christmas. That's the second quantum revolution. The use of non-locality through the construction of qubits, quantum computers, and so on and so forth. That's the so-called second quantum revolution. Again, motivated by Albert Einstein. So, wow, this guy, God. But what can you expect about the current stage of technology and development? Can you expect this little girl will a day work on a quantum computer and play like this? Will take some time. At the moment, I think what you can offer to this little girl is more like a Lego kind of quantum computer, and then she can enjoy to make the Lego. But before she can have the quantum computer inside these kind of things, there will be a very long time. And that's the final words, maybe by assembling this qubit, at some point there is a collapse. We are reaching the macroscopic world, and whatever you do, you will collapse into it one state, and then you cannot further grow, and you cannot make more and more complex algorithms. So reaching 1 billion or even 100,000 cubic logical qubit is very debated. Because as I say, we can make the two-slit experiment with fullerene or with molecules with 3,000 atoms, but maybe not with a cat. Certainly not with a cat, but even not with something much bigger. So the possibility to scale up the quantum computer is also strongly related to the understanding of the collapse of the wave function in a system like this entangled qubits. Okay, that's all. I think I'm done. Thank you for your attention. Question? Now, do you understand quantum mechanics?
Yeah.
Please, raise if you understand quantum mechanics, raise your hand. Nobody, right? Yeah, Jose, you understand better. So, any question? Don't be shy. Everything's clear? No, you don't. Yeah. Good.
The first, like what I'm going to describe between the theoretical possibility of coexistence of states and the fact that there is something very concrete that now you in the deterministic fashion in order to produce technology. When you're making the leap of this technology, you're assuming that there is determinism. Every time you're going to switch the light is going to turn on. Otherwise, the technology is not very validated. So there is an implicit deterministic principle behind this. At the same time, quantum mechanics, as you described, still a debate of non-determinism. And is it only because where is the transition from this inherently non-deterministic principle switching and becoming something very deterministic, whereby we are talking about engineering around?
That's a good question. Actually, the quantum computer is actually realizing what you say, because you have entangled qubits, so you have this non-locality which is complicated, but you can engineer the level of entanglement, and you can make an algorithm on top of it. Basically, what you do with this very big wave function, like in the case of 300 qubit, is that you try to encode a way that you will kill part of the component of the wave function and you will maximize all the parts. It's just like playing with interference inside this huge wave function. So this, they know how to do. So it means that although there is some kind of, the reality of what's going on is for another debate, it's really possible to be very precise in controlling this ensemble of qubits, and then to achieve, and to make a measurement on something that is extremely kind of deterministic, because you have programmed it, okay? It's not just like measuring spin up or spin down, okay? And so it's through engineering that you can, kind of, what do you say, pass this indeterminism and still design something that is deterministic, because the quantum computer, the algorithm, you will have factorization of the gigantic prime number, yes, but you will have a very deterministic effect in a way. You get the response. Okay? So it's that will be not like I want to factorize 10 to the 10 prime numbers, and I will have a random solution. No. Yeah, exactly. So this, I think the determinism comes into encoding, the way to manipulate this qubit. It's not the same as just measuring spin up and down. Mark, question.
And on the technical question, you didn't talk about quantum flagship, and you are probably maybe well positioned to tell us something about that.
Mm-hmm.
So there are many, as you said, the race for technology is being led by industry. It's not the perception. So what is the role of initiative like the quantum flagship with respect to what's happening now in industry, with significantly higher funding? And if you are aware of what is the direction that the quantum flagship is taking?
Mm-hmm. Oh, I'm not. We're not involved in the quantum flagship in. Yeah.
So, but
it's not.
you have to
So, yeah. But I know a bit what's going on. Actually, what has been pushed is to. There were a lot of. I mean, ICREA is French. No, you take most of the pioneer of quantum, also the pioneer of quantum again, were European. So in Europe, you have a gigantic playground for. So a lot of spin-off during the first years of the quantum flagship, a lot of spin-offs have been materialized actually. A lot of companies, a lot of research from labs went to in France there are plenty of spin-offs. So and a lot of investment from the national the countries have been made. So this for instance you have Candela, which is a spin-off related to an aspect where they use photons to make qubits, and now they have been supported by European Commission, and they have a computer with 12 photon qubits. Yeah, but you know people start to use these things. So it's more like we don't have big companies like IBM, Google, Amazon, which are investing a lot of money in order to scale up quickly and to offer their product. But still, there are some. What I've heard is that this kind of technology that France is proposing are in the scale up. What can I say? If you think about scale up, they are more promising than all the Google and stuff, because all these things is related to superconductors, which demands gigantic cryogenic equipment, and it's not scalable. But photonics is very expensive.
It is. I mean, the question is in that direction. In many, when you think about disruptive technology, it happened in outside major industry, right? And then that was what created new giants in technology. They were allowed to develop that. They were allowed to create these new concepts because they had no competitors. But now it's totally different. The giants are already there and they are investing on that. So what's happening to the money that Europe is putting in all of these spin-offs? I'm not saying that these spin-offs are not going to be successful. I'm just saying that from a business perspective, they have 100 times less funding than the giants. And from a business perspective, they are going to be 100 years later than the others. So, I'm a bit surprised.
Because if you take IMEC, if you look at all the giant, Apple and things like that, they use IMEC to develop their new technology and Samsung. So IMEC is really a champion in Europe. Yeah. And IMEC has a program on qubit, on silicon qubit.
Yeah, but it's funded by the big ones. That's what I'm saying. Like
it's funded by big one.
IMEC.
Who's funding IMEC?
Private line on the industry.
Yeah. What do you mean? In the academy?
Of course, IMEC is funded like 80% by industry.
No, I'm saying that in Europe, if you want to think about scale up, and quantum computer, there's not just quantum computer. We have a company like QSI that's doing some kind of random generator and quantum communication. The Chinese, for instance, again, they are dominating the world of quantum communication. They are at the moment, as we speak, they have quantum encryption in signals that travel 10,000 kilometers. So this is a reality. J1 Pan, who is also testing a thought experiment of Einstein, is a guy who is leading all this program in China. So we are doing what we can, but I think we are big competitors. And then so you have to play with your strength. I think the semiconducting qubits is very interesting, because if we find a way to make very good single qubit and entangle them, we have already the platform to scale up, like STMicro, and but okay, it's maybe a giant challenge. And in terms of quantum technology, again, for us, ICN2, as I say, what we do is very fundamental.
So, but that's fine. I'm not criticizing. It was not a criticism. It was just to understand that the competition to
what is the role, for example, of the company that Kilimanjaro?
Yep,
the same. So
correct.
Have few qubits when some other company.
So still like billions,
They're already making thousands.
And this is different. That's what I'm saying.
Yeah. Okay. Situation with Kilimanjaro with it, because they're looking at the different kind of
Technology.
technology in the sense of quantum.
Yeah.
You have to look at each example to see if there's a difference. But once you have a big company developing the same scale in the similar devices, then it's not.
Okay. Let me just give you maybe some new answer. If you will have only IBM or Google scaling up their own technology, at some point in time, it will cost us a lot of money to access this computer. Actually, now they have closed. Initially, they opened for people. Now you have to pay if you want to use that. So it's good to have plenty of alternatives.
Yeah.
And it's good to have Kilimanjaro and to have something at BSC, because then some engineer, they can test algorithm. So I think the diversity of hardware platform is important, because you have more chance to not to be completely out of the game.
The reality is that you're not going to have a company that will develop a superconducting qubits that is going to dominate the market. It's going to have, if there is something important developed by that company, it's going to be bought. Yeah, but for the people are going to be bought by the big ones. I think this is the answer to that question.
Well, you know what I say also in at some point, it's not I'm not invented that, but if for some fundamental reason, after 10,000 qubit, everything collapses and you cannot continue to maintain your algorithm, goodbye. And that's all. And all the investment and everything will collapse immediately. That's a big question. When you ask this to Anaspe, he's very cautious because they don't know. Again, I say I'm taking the analogy about the Young, two-slit experiments. You can make 1,000 atoms, you can make a slit, but if you take maybe 100,000 atoms, you will not have this interference. It's gone. So what about these billion qubits that you need to do something which is very practical? So that's a very serious question. Now people just put on the carpet because we have not yet found that. There is also decoherence and the qubits just hundreds, a few hundreds. But maybe at 1,000 or at 10,000, you have no way to control the collapse of all this stuff. And then the things is completely.
So it's nice that you're talking about that wave function collapse, and at the same time you're using the word collapse.
Quantum collapse. That would be the collapse of their technology. But that's a question that people discuss because well, why should we have a billion of qubits even at very low temperature or not collapsing? Like CPUs, but that's really, I think it's a question. But of course they don't have them. They are just like orders of magnitude. And in the meanwhile, they make money because IBM sells its computer, at San Sebastian in Germany. They make money, the people pay, but they also try to learn how to use this small number of qubits to do something or to make some communication and so on. So I don't think, frankly, for us, it's for us to say it's not somewhere to. I mean, it's not very. I will not bet my money on that. I mean, if we have to do something, it's to develop artificial intelligence. And this is more like a business.
I think that quantum already changed the way we do things. Because you think of this screen, everything is based on quantum phenomena. So I think that beyond a quantum computer, there's still a much more to be, or in addition to a quantum computer, there are all other applications that, it's sensing in many of the areas, right?
Also, in bio, there are some like photosynthesis or the eye of the bird, the compass. So maybe you can mimic something that you think is quantum, but you make a new technology, guiding drones or other stuff.
No guiding drones.
Wait for that. Okay, no more question? It's late, no? No, it's not late. More question? Yeah, you have always a key question. Question?
So if no more question, thank you, Stephan, and thank you everyone for coming. Just a comment. Our idea is this is the first talk of a ICREA Prof series. So if any of you is interested in share your research or talk about your field, please let us know.
Never. Quantum politics. Quantum politics. Yes, I don't know what happened. That's right. Yeah. So you emotional like the quantum. I'm putting down the accusing political statement. Great. How are you? I use resources and solve problem.
No, I'm on fire. I'm doing blood analysis and then so what do you do? You go back to Greece now? Tomorrow, what about are you trying? No, I'm saying. Okay. Thank you.
De hecho, los de Esteban han venido a la universidad.
No. No tengo idea.